Okay, thanks for the introduction and the invitation, Ephraim, to CQuick. It's a privilege to kick off the conference this year. So as Ephraim said, my name's Raj Patel. I'm a UKRI Future Leaders Fellow at Imperial College, and my talk is titled Gaussian Boson Sampling Experiments with Displacements and Time Bin Encoding. And there are various people that made this work possible. Santi, Guillaume, Bryn, Yunshik, Steve Korthammer, and Ian Walmsley. But in particular, I want to highlight the fact that this work is largely driven by Santi and Guillaume, who did all the hard work. Guillaume also has a talk on Friday morning, an invited talk, so please check that out as well. Okay. Sorry, the animation is a bit slow due to the Zoom streaming, but it should be. Okay, so I will provide an outline of my talk. So the talk will essentially consist of three parts. First, I'll introduce the Gaussian boson sampling task, and I'll also talk about a few applications. Then I'll move on to the meat of the talk, which is really just discussing how we would go about performing displaced Gaussian boson sampling. We'll see that this can potentially help us to round out the Gaussian boson sampling toolbox. And then I'll move on to another experiment that we did in our group, where we search for dense subgraphs with a time bin encoded GBS experiment. And then I'll finish with a summary. Okay. So just to provide an introduction to Gaussian boson sampling for those who may not be familiar with it. So GBS was first proposed by Hamilton et al. In this PRL paper in 2017. And you can consider it as a generalization of standard boson sampling. It's a non-universal model of quantum computing. And here we're considering using, thanks. Better? Here we're using single mode Gaussian squeeze states instead of single photon Fock states, which is typically used in standard boson sampling. And the idea is you take these quantum states, you interfere them non-classically in a linear optical network consisting of beam splitters and phase shifters, and then you measure then you sample the output distribution from this network. And so pictorially, looks something like this. So we have a number of single mode squeeze states at the input. Here's our linear optical network, which can be described by a unitary matrix U. And then we count the photons at the end, count the photon distribution at the end. And so the output can be characterized by a 2m by 2m covariance matrix, capital sigma. And the matrix elements of sigma consist of elements which depend on the annihilation and creation operators. And in this expression, we also include this displacement as well, which is the focus of the next section. And so the output photon number distribution is given by this expression here, where little p vac is a probability of measuring vacuum in the modes, in the output modes. And this function here is the Hafnian function, which is the matrix function which lends the complexity to Gaussian boson sampling. So inside this argument here, we have AN. AN is a submatrix of this matrix A, and A depends on the identity matrix, and also this covariance matrix of the Q function, as shown here. And so AN itself is a submatrix formed by repeating various rows and columns Ni times. So Ni is the number of photons measured in a particular mode. And AN has the size of 2n by 2n. And the size of this matrix therefore increases with the number of detected photons at the output. And so one of the features of this Hafnian function is that it counts the number of perfect matchings of an arbitrary graph with an adjacency matrix A, and it's given by this expression here. So perfect matching is shown in this example here. So here we're dealing with 4-node graphs. And a perfect matching is a case where a vertex has only one edge with a single neighboring vertex and no other connections. Okay. And so what happens when we want to add displacements to Gaussian boson sampling? Well, in this scenario, we move on from the previous expression of the photon number distribution I showed just on the previous slide, and instead we have to calculate this loop Hafnian, where a tilde n has diagonal repeat elements from this this quantity here, which depends on on the displacement vector. And we can take this loop Hafnian and we can expand it in terms of these different terms here. And we see that there are three contributions that we can identify. The first term is where all photons come from the squeezed light source plus the thermal state, maybe due to some loss. The last term considers all photons just from the coherent state, and this middle term considers interference between squeezed states, thermal states, and coherent states. And so I talked about complexity. It turns out from the conjecture of permanence, which is used to justify the complexity of standard boson sampling, the output distribution of a GBS device is also sharp p hard to compute. Okay. So Gaussian boson sampling has been a hot topic for the last couple of years. In particular, there's been some very nice experimental work from USTC, from the group of Chaoyang Liu and Jianwei Pan, where they demonstrated quantum advantage with a sort of a free space architecture using micro-optic interferometers. Chaoyang Liu, I believe, is giving a talk remotely this week, so be sure to check that out. And in their experimental work, they utilized up to 144 modes and measured up to 113 photons in a single sample. And you can see the engineering effort that goes towards achieving this goal in bulk optics. You've got the interferometer itself sits in the middle, and you've got all these optics used to couple light and direct the various beams and compensate for some phases. And more recently, there's been a report from Xanadu where they demonstrated quantum advantage using a time bin interferometer. This utilized 216 time bins, up to 219-fold detection events with photon number resolving detectors. The system is or will be accessible via the cloud, and they utilize some of the latest loop Hafnian algorithms that have been developed at Imperial in my group in collaboration with Bristol and Hewlett-Packard Enterprises. And Nico will be giving a talk on this work on Wednesday. Okay. So in terms of applications of GBS, there are quite a few compared to standard boson sampling. For instance, molecular vibronic spectra calculations with Frank and non-Condon factors, molecular docking, optimization algorithms, and solutions to various graph problems can be enhanced by Gaussian boson sampling. And a lot of these examples have come out of Xanadu. Right, so coming to GBS with displacements again. So displacements of a multimode Gaussian state from a GBS device has various uses. I mentioned one of them, molecular vibronic spectra calculations, but they can also be used for measuring the similarity of graphs. Furthermore, displacements are required to perform more general operations on states in phase space. For instance, if you want to engineer some quantum states, these typically rely on operations which involve displacements, and some examples of this include GKP states. But up until now, experimentally, no one has demonstrated GBS with displacements. And that was the focus of this next paper, which I'll highlight here. This was published a few months ago. Guillaume is in the audience. And in this paper, we take a two-mode squeeze vacuum and a coherent state, and we mix it in a 15 by 15 multiport interferometer. And we do two things. First, we do in situ reconstruction of the 15-mode output Gaussian state using displacements. And in particular, we only use 3 measurement settings to do this reconstruction, so far fewer than the dimension of the system. And then finally, we study the effect of coherent light on the complexity of sampling from the output probability distribution using some semi-classical models. And so here's a scenario. I've got the picture up here. So we've got single mode squeeze. We've got squeeze vacuum, single mode squeeze states here, and we have our lone coherent state in the bottom here. And so what we want to ask is, can the quantum state of the output be reconstructed? And so in single mode CV quantum information, typically the way you do this is you interfere the unknown state on a beam splitter with a coherent state. This is just homodyne tomography. And then you measure the outputs, you can perform a reconstruction. For a multimode CV state, what you do is you take each individual mode and you interfere it with you take each individual mode of the unknown state and you mix it on a beam splitter with a coherent state, and you do joint measurements of the output. And so in what follows, we will assume that the output state is Gaussian and that the imperfections in the GBS device are small enough to approximate the output statistics well. And so to do this reconstruction, we need to take into account the A matrix and also the displacement vector. And it turns out that the A matrix can be written in this block diagonal form, where where B is a symmetric matrix and C is a Hermitian matrix. And if C equals 0, this corresponds to a pure state. And so I've also listed here again the expanded loop Hafnian, and you can see it contains terms that we're interested in. It's got these terms involving displacements. And so from this expression, we can point out some single and joint two-mode measurements that we can perform to perform this reconstruction. So what we want to do is we want to calculate these matrix elements of B and C. And the way we do that is we calculate the probabilities which depend on those elements. And so we can separate these into 2 classes. One set where we don't have a coherent state, and a second set of measurements where we do have a coherent state. And in this expression here, we have this phase term which can be controlled by altering the phase of the local oscillator or the coherent state that we inject in the system. And so by doing this, we can obtain all these other terms, aside from the sign of the imaginary part of this matrix element CJK. And it turns out you can obtain this through an additional measurement where you simply take the coherent state and you inject it in a different mode of the interferometer. Okay, so the experiment looks like this. So I'll just walk you through it quickly. So here we have a 1550 laser, which produces pulses of length 100 femtoseconds. We split it on a beam splitter. One arm goes into a Piplin waveguide to perform second harmonic generation to 775 nanometers. This serves as a pump beam for the next down conversion stage after being filtered to produce uncorrelated spectra. And so here we have our PPKTP waveguide, which we pump with the 775. We generate the squeeze state, the 2-mode squeeze vacuum, I should say, which we separate on a polarizing beam splitter into 2 separate spatial modes. And that goes on to the next step, which I'll come to in shortly. And then the other arm serves as a local oscillator. So we attenuate it using an ND filter, we use some bandpass filters, and then there's an optical delay line to match the temporal, to match the time of the squeeze states that we're sending into our boson sampler. And so in addition to this delay, you'll see in the back here, there's a phase modulator. We use this phase modulator to actively phase lock the phase of this LO with respect to the 2-mode squeeze vacuum. And you can see we're able to lock this phase to pi/4 over a duration of up to a minute and beyond. Okay. And so that's what the paths look like. And so we take those these three beams and we send them into this system over here. So here we have a passive interferometer on a silicon on-insulator chip. It's 2 millimeters long, and it's a 15 by 15 unitary. And so we send the photons into the chip, and they interfere, and then we couple them out using fiber. Okay. And so the action of the chip can be described by a transfer matrix T, and we obtain this simply by taking light and sending it into each mode individually and measuring the output. That gives us this top matrix, which corresponds to the absolute value of the matrix elements, and the arguments of the matrix elements can be obtained through 2-photon interference by sending light into pairs of modes and measuring joint detections of the output. Okay, so that's the setup, and then finally we perform photon detection using superconducting nanowire detectors. And so I should state that we're always trying to operate in the collision-free regime so that we can use click detectors. And the collision-free regime simply means that we don't detect more than 1 photon in a particular output mode. Okay, so here are some results of the reconstructed state. Here's the A matrix. So the absolute value of the 8 matrix elements is on the left, and the arguments of the matrix elements are on the right. And below we have some residuals. And so in these measurements, we used a 1 milliwatt pump and a mean photon number from the down conversion of 0.01 and size of the coherent state given by 0.19. And you'll notice that the diagonals are missing in these matrices. That's because we don't have photon number resolution, which is why we can't measure these probabilities PJJ. And so having done this using this state reconstruction method, which we call the direct method, we want to compare it with an indirect method. So the indirect method we choose is to measure various parameters of the experiment independently. So the T matrix, the squeezing parameters, the coherent state and the losses, and we feed this into some code written in Strawberry Fields by Xanadu, and we can produce what the expected photon number distribution should be. And so for the A matrix determined by these 2 methods, we can calculate threefold statistics using the loop Hafnian, and then calculate the total variational distance, which serves as a measure of how close they are to the theory. And we see that both methods are pretty close in that the distance is almost 0. However, while both methods perform well, the direct method can be performed in situ with far fewer measurements. Okay, so looking at this figure here, we have some 4-fold statistics from the displaced GBS experiment. The experimental data is shown in blue, and the theory from calculated from using just the loop Hafnian with no imperfections is shown with no imperfections or approximations is shown in orange for zero coherent state and for a coherent state of size 0.15. And you can see that the predictions match the experiment fairly well. And so furthermore, we can increase the size of we can vary the size of the coherent state, and that's what's shown in this orange plot here and the triangles. And you can see that as D increases, we see that D increases as a relative contribution from the squeeze states compared to the coherent state increases. So as we reduce the size of the coherent state, where we expect to get more photons from the squeeze state, we actually see the distance increase. And we believe this is due to some distinguishability with our squeeze states, which aren't included in our model. Okay. And so we have, this plot shows 2 extremes. There's the full quantum model. This model is calculated from the loop Hafnian, and then there's a classical model which we use thermal states and send it into a system, a theoretical system. We calculate the distance. And so we know that the complexity of GBS arises from the calculation of the largest Hafnian from the loop Hafnian. And this scales with the number of photons n. And so we expect as we increase the number of photons, which we can do by adding more coherent light, we should be able to, one would think naively that we should be able to achieve some increased complexity by doing so. And so what we do is we consider various models which may be used to approximate the data. And so, as I mentioned, we use classical models shown by this black data here. And here we're considering displaced squeeze thermal states that best approximate the experiment. And the full quantum model is simply just a calculation of the loop Hafnian with no approximations. And in between, we consider a semi-classical model, which we call the kth order approximation. And here we truncate the loop Hafnian to order k, where k is roughly the number of photons arriving from the squeeze source. And we can see that for increasing degree of k, for increasing order of k, we see a better match with the full quantum model. Okay. However, if you increase the size of the coherent state even larger, then it may be actually more efficient to perform a different type of test. So we perform a likelihood test on the data rather than calculating the TVD. So the likelihood ratio L is given by this expression here. Here, B is a model, which is a full quantum model, which we keep fixed throughout the tests. So each time B corresponds to the full quantum model. And on the top here, A is an approximate model that we're considering. And the idea here is that if L is less than 1, the full quantum model is actually a better description, and the squeeze and the statistics are more likely to have come from squeeze states rather than thermal states or coherent states. And so on the top left, we show the n-fold probability as a function of the size of the coherent state. And you can see as we increase the size of the coherent state, it's more probable that we measure an n-fold probability for n equals 5 to n equals 9. And on the top right-hand corner, we plot this likelihood ratio as a function of the size of the coherent state. And we see that the validity of the kth order approximation improves for larger coherent states. So as we increase the size of the coherent state, we see that we're deviating more from this zero value here. So here, k equals 4 corresponds to a better approximation compared to, say, k equals 3 or the classical model. Yes, we also show that the validity of the kth order approximation improves for larger samples. So if we take a slice of the data down these two curves here, corresponding to 0.6 and 2.2, and we plot out the number of samples, we plot out the likelihood ratio as a function of the number of samples. We see that for more samples, as one might expect, the approximations perform better. But in particular, the k equals 4 approximation performs the best. Okay, so that concludes the displaced GBS work. I'll now move on to finding dense subgraphs with a time-bin GBS interferometer. So as we saw in the previous slide on the applications, we know that GBS is well suited to solving, or at least enhancing enhancing the calculation of certain classes of graph problems. And so in particular, the one that we're focusing on is this one by Arizola and Bromley from Xanadu. They showed that GBS can be used to enhance the search for dense subgraphs of a graph. And this problem is NP-hard, and you can see more in their paper on the theory behind this here. And here on the right-hand side, I've just included a cartoon of sort of what we're talking about. So here we have a graph, and you can see this section here seems to have a larger concentration of edges. And so this is sort of the dense subgraph that we might be interested in looking for. And so why might you be interested in this? Well, there are applications such as analyzing communities within social networks. It has applications in bioinformatics. And apparently it's also being used for fraud detection. And so in our work, we use a time-bin encoded GBS device to find the most dense 3 and 4 mode subgraphs in a 10-node graph. And this work is on the archive here, paper by Santi. If you'd like to see more, DOIs are also at the bottom here. Okay. So we know from graph theory that graphs can be described by an adjacency matrix, capital delta, with elements delta ij. And each delta ij provides a weight to the edge connecting different nodes ij of a graph. And for an undirected graph, delta ij equals delta ji, and we say that the adjacency matrix is symmetric. We know for a pure Gaussian state with no displacement, the A matrix looks like this, which can be written in this form. And in particular, the photon number probability distribution, which depends on the Hafnian, can be written like so. And so here, Bn is an n by n matrix corresponding to the adjacency matrix. And this is very similar to what we do in a Gaussian boson sampling type of experiment. We can isolate the symmetric matrix from our photon statistics, and this can correspond to the adjacency matrix of a graph. And so the density of a graph is defined by D, where we essentially perform like a normalized sum over all elements of delta ij of the adjacency matrix. And the Hafnian of the adjacency matrix counts the number of perfect matchings of a graph. And we can think of this as an indicator of the density of the graph. Typo. And so for our work, we produce a recipe for obtaining these dense subgraphs. So the procedure goes as follows. First, we decompose the B matrix into a unitary operator U, describing a linear optical circuit and a set of squeezing parameters. Then we take this unitary operator and we find a set of beam splitter ratios and phase shifts which can be used to construct it. We rescale the squeezing parameters by a constant C, and this is just to improve the n-fold detection rates and has no effect on the relative contributions to the photon number distribution. And then we generate samples using our GBS device, and this can be described by this expression here. And then we take these samples from our GBS device and we supply it to a classical algorithm, which can run in polynomial time to find the dense subgraphs. Okay, and so a bit of an introduction to time-bin GBS. So we saw the Xanadu experiment has also utilized time-bin GBS. And it's very attractive for several reasons, which I'll come on to it in a second. So with this architecture, we can encode any arbitrary unitary, and more details about this type of architecture can be found in this paper by Keith Motes. And so the way it works is we take a train of squeezed light separated by a period tau p, and we send it into a switch, S2, which switches the light into this loop here, which we call the storage loop, and it has a storage time of tau s. We can then configure this unitary S1, which is a variable beam splitter, which performs the processing. So this performs a non-classical interference, which we want to do when we do Gaussian boson sampling. And so the bottom loop is connected to this top loop, which we call the processing loop. And this does the interference. It has a phase shifter, which can be set, and its delay is matched to the repetition, to the period of the pulses here. And I should say that the nice thing about this architecture is that it's very resource efficient, right? So we only have one squeezed light source, we potentially only have one detector, and we can essentially scale this architecture up to many time-bin modes simply by increasing the repetition rate. In our work, at the time, we didn't have fast switches available to us, and the ones that we had available to us were a bit lossy. So we considered a more simplified architecture, which showed the proof of operation. So here we consider a static single loop, essentially, you can think of it as taking this loop here and shrinking it down to 0, setting this switch to unitary, to identity, so that we just have a single loop as our processing loop attached to this line here. And so naturally, with this system, we no longer have the ability to dial in arbitrary unitaries. We're sort of fixed by the beam splitter, by the single variable beam splitter that we have in the circuit. And so on the left-hand side, this shows a circuit diagram of a 6-mode system and the various beam splitter operations between the various modes, which map onto the time-bin interferometer. And a simplified view, omitting the input and output modes, is shown here. Right, so again, the experiment's somewhat similar to the previous one I showed. Instead, this time, we don't have a 1550 laser. We use a 775 nanometer TISAF laser, clocked to 80 megahertz. And then we send it through this setup here. So this is a this is a pulse picker based on a Patel cell. Patel cell is just a birefringent material which we can switch polarizations by applying an RF signal to it. And so we send it through this Patel cell, and we actually double pass it. And the reason we do this is because our detectors have a dead time of 60 nanoseconds, and the laser is producing pulses at a too high repetition rate for our detectors. So we're going to carve out bins of pulses which we use in the experiment, and we reject the rest. And so that's shown here. So we see a series of peaks separated by 12.5 nanoseconds, and we carve out a group like this, which we send into our interferometer. And so we could take these individual signals and we interfere them inside the interferometer, and we reject these. Okay. And so similarly, we send it through a PPK2P waveguide. We generate squeeze states. Here's a JSI. So for a pure state, this should be nice and round. And we perform Hongo-Mandel interference to show that we have good indistinguishability. Here, it's 85%. And so we take a 2-mode squeeze vacuum, we separate it on a beam splitter, and we send it to 2 ports of a fiber beam splitter, shown on the right here. And this is connected to our single loop time bin interferometer. So this consists of, so our signal comes in here, we have a variable beam splitter here, and so the signal is sent with some probability into this loop. The light comes out, it goes through a delay line, goes through some optics here, and we collect it into this coupler here, and then we can potentially cycle it back. However, we don't have active switching, so this is a completely passive circuit. This mirror here is connected to a piezo, which we use to do some active phase stabilization of the loop. Okay, and so the light is sent eventually through this device here. This fans out the signal to 8 detectors, which we detect using SNSPDs. And the reason we do this fan out is to avoid this reset time of each individual detector. Okay. And so the action of our circuit can be modeled by this transfer matrix. You'll notice that only the upper portion of the transfer matrix has elements. That's because the interferometer doesn't perform an arbitrary unitary. So you can think of this, the reason for this is because a photon in one time bin cannot interfere with a photon that's already been generated in a time bin prior to that. And so we have this limitation, and due to the limited connectivity of our interferometer. But we do have a variable beam splitter, so there is some programmability that we can achieve. However, for our purposes, we just set it to 50-50. The A matrix looks like this. And you can see that we no longer have these quadrants here equal to 0. So there is some mixedness with our state. And I should just reiterate that that's theoretical data based on modeling of our experiment. And here you can see the photon number distribution. So you can see a group of statistics, each corresponding to a cycle that we carve out from our train of laser pulses. And we look at the 2-fold detections and 3-fold detections for various different output combinations. And you can see that the experiment in orange matches the theory in green quite well. And you will notice that there is a decay in the, there is consistently a decay in the probability for each set. And that's because of the fact that we don't have an active switch switching photons into and out of the interferometer when we want. It's just a fixed beam splitter. So each cycle of the photon as it goes through the interferometer will incur some loss. Okay, and so having generated those samples, we can feed it into our classical algorithm. And so here we're looking at, here we identify a 10-node graph given by these vertices, these blue vertices within a 20-node graph. And within this 10-node graph, we can obtain, so within this 10-node graph, we obtain the dense subgraphs from the symmetric part of the A matrix. So even though there's some mixedness there, we can still take the symmetric part and see if we can identify some dense subgraphs. And you can see in this bottom portion here, there looks like there are 3 and 4 vertices which have a higher density. Okay. And so here in this figure, we plot the mean density as a function of number of samples. So as we draw more samples from the GBS device, we see that we are able to find the highest density subgraphs, and they eventually converge. And so this is despite the impurity of the state and the total efficiency of the system, which is around 10%, which adds to this impurity of the Gaussian state that I mentioned. And we actually see for higher squeezing values, so actually let me just point a couple of things out here. So this brown curve here is the ideal data, which we calculate theoretically. So this is what we'd expect ideally. And the purple curve here is what one would expect using a classical uniform sampling algorithm. And so you can see our experimental data sits in between. So there is definitely some enhancement despite the impurities. However, you'll notice from the squeezing parameters here that actually when we increase the squeezing, we actually see a decrease in this sort of the rate of this convergence. So for instance, the green curve here is actually lower than the blue curve, which corresponds to a lower squeezing value. And in the paper, we go on to discuss how this might be contributed to due to the loss in the system, and that squeeze states are more sensitive to this loss. And just to summarize, we've performed the first demonstrations of GBS with displacements and experimental study of the search of dense subgraphs. Displacements are quite useful for many applications, as well as general Gaussian general operations in phase space. We've developed techniques to characterize the Gaussian states in situ. We perform time bin GBS, and this architecture is very favorable for its limited resources that it consumes. And GBS offers scopes to help solve a variety of graph problems, which may open up more real-world applications for GBS. And with that, I'll say thanks, and I have positions available if you're interested.